Greg Zelik, I hope I pronounced that correctly, will actually be on Wednesday and swapping out from Wednesday to right now is Karl Zelik from Vanderbilt University. So, and I'll let Karl introduce his team.
Awesome, thank you. All right, thanks so much to the conference organizers. Thank you to Greg Zewicki's lab for the switch. Due to unforeseen circumstances, I need to be departing tomorrow, so unfortunately won't be here. I'm really thankful to be able to give this presentation today along with Matt and Eric. These are my original PhD students. They helped me set up the lab 4 years ago. They're both getting closer to graduation, and so this might be the last time we get a chance to do this. Our lab is a part of a center focused on rehab engineering, so about 90% of what we do is try to advance science and technology in order to help individuals with disabilities. About 10% of the time is spent trying to think about how to turn ourselves into superheroes. Unfortunately, unlike Thor, I'm not a god from another planet. Unlike Tony Stark, I don't have the wealth or knowledge to create Iron Man yet. And whatever the Hulk is, I'm not signing up for that. So we're thinking about how to create turn ourselves into everyday superheroes. This is our first project, trying to recreate superhero flight. Has not gone particularly well. This is as far as we got. And so we broke down to a simpler problem. I thought about what are my everyday struggles. Well, I have a 2.5-year-old son. This is my son, Dex. He insists on getting bigger. He's destroying my back. And so I just would like some kind of suit that helps offload my back and reduce the wear and tear. What my life is like, it's a lot of bending over, getting kids in and out of car seats, helping them at the sink, playing with them on the ground, so I need to have versatility of movement, trying to be an adult on the weekend, gardening, staining my porch, things of that nature. And then during the week, it's being a professor, which means a lot of sitting at a chair, answering emails, writing, reading, thinking, and occasionally getting hungry for some data and running down the hall to see what my grad students are up to. So we started thinking about how to turn ourselves into everyday superheroes. I need a device that fits into my own life. The very quick summary of this, we were working on it for a couple years, is I went and looked around at exoskeletons for industry. I got insanely jealous, and I just selfishly wanted something that would work for me. Everything was too rigid, too expensive, too cumbersome. So we went back and looked at the science of what's causing loading on the low back, created a wearable clothing-like device, which is essentially a spring that acts along the back, and published a paper that provides the theoretical basis and shows an 8-subject experiment showing that it can offload the back muscles. And we ultimately ended up with something that looks like this, which is a clothing-like device, springs along the backside, and a little clutchable motor, motor-driven clutch that allows us to engage and disengage it, so I can sit as a professor, and when I need to go lift something heavy, I can walk over and engage the assistants. The reason I introduced this all is just to say during this process, I realized even though it was a completely selfish endeavor to begin with, there were a lot of other folks who voiced interest in devices that would fit underneath their clothing, people who didn't want to be seen as wearing something in their daily life. Nurses are an example, yet they're at an occupation that's at high risk of developing back pain. There's other folks in industrial settings where they may be around machines or conveyor belts, and so it may be dangerous for them to have elements protruding from the body. So this is all just a lead into what Matt's going to talk about, which is something we haven't presented before, which is taking some of these same concepts, fitting under the body, or fitting under the clothing to assist the ankle.
Thanks, Karl. So we're pretty excited about this concept of putting exoskeletons underneath your clothes, and so we realized we could use it for other things besides the low back, in particular ankle exoskeletons. So there are a lot of really cool devices for ankle exoskeletons augmenting human movement, many of them designed by people in this room. One of the things, though, is that they can be really hard to use in a practical situation. So if someone's out in public, they might not want to be seen as a cyborg, where if you can see or hear their device, and it might be difficult to drive your car or descend stairs. So we got to thinking, what would we need to make an ultra-low profile exoskeleton for ankle assistance? And so we started with some key ingredients. One is we wanted to assist during stance, which is taken directly from a previously successful ankle exoskeleton by Karl Zelik and Zewicki. We also wanted to incorporate an exosuit style interface, so it would be low profile. We could conform to the shank segment. We could eliminate a rigid ankle joint. Third, we wanted to use a body weight actuated clutch or engaged clutch. And the advantage of this is we could make the device both passive and intuitive for the user to use. Now, this is what we ended up with after countless prototypes. And so it's comprised of 3 primary pieces. We have a shank interface that conforms to the shank. We have a stiff assistance spring and an under-the-shoe clutch. And this not only fits underneath clothes, but provides passive ankle torque assistance during stance to offload the calf muscles. Now, one of the key pieces is this shank interface here. It turns out that though it looks simple, attaching to soft tissues is a very tricky problem. So we spent a lot of time experimenting, trying to find something that would work. We settled on this device, which uses a prosthetic liner material, which conforms to the shank and grips the skin. And then this specialized inextensible wrap, which can be thermoplastic or nylon fabric. And that does two things. One, it spreads the forces around on the shank and uses a specialized geometry so that we can support these assistive forces without letting the interface slip down the leg. So this means we can be low profile, we can have no rigid ankle joint, all comfortably supporting these assistive forces. Next, we have the under the shoe clutch. And so the primary function is provided by these two rubber grippers that impinge on this slider when body weight is compressing the clutch. And that allows us to clutch during stance and unclutch during swing. It's about 5 millimeters thick assembled, a little bit less than 200 grams. It's also silent and adapts to different speeds because it's operated based on body weight during stance. So the way this works is during stance, body weight compresses the clutch, impinging on this slider, which can't move, and so now the big extension spring can stretch and recoil, giving you that assistive torque. And then during swing, when body weight is off of the clutch, now this blue slider can move freely along with the assistance spring, and all the user has to resist during swing with their ankle is this really tiny, weak rubber band-like green spring. So it looks something like this, so they don't feel anything, allowing their ankle to move freely. There it is. So this is a video of the device in action. So as the foot comes in contact with the ground, the clutch engages. The stiff assistance spring here stretches over stance, giving you torque assistance. And then as the foot comes off the ground, it releases and the ankle is free to move. So we did a single subject case study, walking level ground with the exoskeleton. On the X here, we have stride percentage, and on the Y, we have soleus activation. So wearing the device versus not wearing the device, we got EMG reduction during stance, and over the entire stride, about a 17% reduction. And we think this could be useful for populations that have reduced plantar flexion torque, or perhaps even healthy users who want to reduce their walking costs long term. Okay, so the first half of my talk was about translating technology now here at Dynamic Walking 2018. But what about Dynamic Walking 2050, right? So what are we going to be talking about then? We'll be hosting it on at the Elon Musk Center on Saturn's moon of Mimas, pictured here, although conspiracy theorists tell me that that's no moon. So what are we going to be talking about, and what are we going to be concerned about in that year? Well, welcome to Dynamic Running and Jumping 2050, where everyone shows up in Ironman suits and everyone still hates music by Nickelback. So what we're going to do is wonder, okay, what is preventing us from having good assistive device technology at that time? One of the things could be interface dynamics. So the physical interface is a transmission between your exoskeleton and your human. And that's important because they can modify the impedance of your system, changing the magnitude of your assistance, the timing of your assistance. And so one idea is to take those interface dynamics, model them, and then include them in our controllers. Now, what I don't know, and why I'm here, is asking, is that useful or helpful or necessary in our future controllers? So let me introduce you to Andy Daiwer on the left here. This is Chris Pratt in 2009. Then Chris Pratt on the right in 2014 as Star-Lord. Now, why this is important is imagine we take an exoskeleton and put it on our friend Andy at the morning shift at the factory. He used the exoskeleton, it's all wonderful, and then we take that same exoskeleton and controller and put it on Chris Pratt as Star-Lord in the afternoon shift. Same device. The controller might not perform as well because we're changing the soft tissue dynamics it's encountering in the work. Okay, here's some other examples. For instance, in low power tasks with low speeds, you might not care about interface dynamics because they might not be very apparent. But as we start doing things like sprinting or jumping or skating, those dynamics might become more apparent. So therefore, they'd be more important. It's also essential for safety of the user. So because they modify timing of assistance, they can end up tripping the person they're trying to help if the interface dynamics modify that too much. So we wanted to quantify these interface dynamics, so we did a pretty simple experiment where we had a subject wear an interface. We excited that with a force measured with a load cell, a displacement measured with motion capture relative to the body. This is the profile here with time along the x-axis and force in newtons along the y. It's increasing frequency chirp signal, and when you do that, you get this displacement where x is along the x-axis and displacement along the y. So what we wanted to do is use a simple model to describe that. And this Zener model is the simplest model out of the ones that we tried that seemed to match the dynamics well. And we found some parameters for that, and then we estimated what that model would do, and it seems to capture the major dynamics fairly well. Okay, so why you care? So here's our friend Andy again. He puts on the exoskeleton. Now imagine this exoskeleton, as it comes in for his shift in the morning, can actuate his soft tissues, and then figure out what that displacement is, and then estimate his soft tissue dynamics, and then custom tune his controller automatically for him. And then a twin Star-Lord comes in the afternoon, puts on the same exoskeleton, can also auto-calibrate to him, which could be a very useful feature. So in essence, what I want you to do is today, think about how to fit exoskeletons underneath clothes, and in the future, consider the implications of interface dynamics for exoskeleton performance, as well as individualizing control. Speaking of individuals, and I'll pass it off to Eric.
All right, thank you, Matt. So today I'm going to talk about the broccoli conundrum of assisted devices. So broccoli is a healthy, nutrient-rich material that is objectively good for you. Now, all reasonable people will agree that broccoli is subjectively bad. Now, I'm going to talk. Now, in biomechanics, we come across biomechanical outcomes that are objectively good, but could be subjectively bad. So two objective measures that are often examined in biomechanics are push-off and collision. So in models, increasing this push-off can reduce collision and can improve the economy of walking. Now, this is potentially relevant for persons with amputation who have reduced push-off. Increasing this push-off could reduce collision and could improve the economy of walking. So one way to influence this push-off and collision is to use robotic prosthetic ankle. This has been shown to increase the push-off and decrease the collision on the opposite limb. But now, are there less heavy mechanisms and more cost-effective solutions? So walking models that have integrated toe joint have shown a reduced collision and improved economy of walking versus a non-toe joint walker with the same foot length. So toe joints have been integrated in some robotic simulations and robotic and prosthetic feet, but they haven't really explored the space all that much. So there kind of remains an open question as to which of these parameters are really important. So we could look at a lot of different parameters. So we could look at toe shape, stiffness, length, axis of rotation, or range of motion. And so we want to perform just this characterization study to look at some of these parameters. And for the purpose of this presentation, I'm just going to focus on how these toe joints can influence push-off. So we performed a systematic study using this prosthesis here. So we can look at a bunch of different parameters with this prosthesis. Say toe length, foot length, toe shape. And we did that with able-bodied subjects, just walking on a treadmill and then looking at inverse dynamics and kinematics. And so one of the first parameters that we looked at was toe joint stiffness here. So we looked at center of mass push-off with varying toe joint stiffness. So we had 0 toe joint stiffness on the left, going all the way up and going to infinite toe joint stiffness, so locking out that toe, with some medium stiffnesses in between. And so we saw at this infinite stiffness, we had maximum push-off, we think good. But actually, 9 out of 10 subjects did not prefer this condition, which was really interesting because we think like maximum push-off better for the subjects. So next, we looked at toe and foot length. So now instead of the toe joint stiffness, now we have foot length there, and we varied foot length from 26 to 32 centimeters. And we also looked at toe length from 5 to 9 centimeters. I'm just going to focus on the foot length here because the toe length didn't really have that much variability in the center of mass work. So once again, we saw this increasing trend here with foot length with respect to the center of mass power work. And at this maximum foot length, we saw again this interesting trend that subjects did not prefer it. So some described it as it felt a little too long, or it felt like flippers, or they were just overall displeased. So this kind of connects to some prior literature and the fact that when Adamczyk and Kuo looked at the effects of foot length, but without an articulating ankle or toe, they discussed that the longest foot length that they looked at provided discomfort due to the hyperextension torque at the knee. So where does that kind of leave us as a community? So we can build, as a community, we can build these prototypes, and we can quantify these biomechanics. But what happens when these biomechanics don't line up with subjective preference? We kind of come to the broccoli conundrum of assisted devices. And just as a quick anecdote, although the flexible toe joint did not provide the maximum push-off or minimize the collision, people did prefer it. And so we're still looking into why they would prefer that. So now I'm going to pass the talk off to Karl, who's going to go up the foot to the ankle.
Okay, so we're going to end this talking a little bit about that lump of flesh and bone beneath your ankle. My first dynamic walking conference was in 2008, 10 years ago, and if there's one thing I've learned about dynamic walkers, it's that you all really like ankles. I'm a part of this. So from our simple walking models to our musculoskeletal models to our neuromuscular models, we use ankle to inspire devices, exoskeletons, prostheses, walking robots. We talk a lot about ankles, occasionally about feet as well. Whenever we're studying ankles in the lab, if we bring folks into the motion capture lab, we put markers all over their shank, we put markers spread out over their foot. We treat these segments as rigid bodies. We integrate the motion of these rigid bodies with force measurements from force plates, and we just apply Newton-Euler equations to estimate moments and then powers and work performed about joints such as the ankle. So one of the things that's interesting historically is this is basically the same process that's been used since 1895. So back when Braun and Fischer did the first 3D motion capture, they'd wait until the middle of the night. They'd attach these electrified Geissler tubes to each limb segment, and they'd track the motion of the limbs in space. So what has caught my attention over the last year is that this assumption of a rigid foot model, it seems very innocuous, it seems very common, it's something that's used extensively throughout the motion capture literature throughout the world. In a nutshell, here's the problem. The foot is complicated, there's motion within the foot, and if you treat the entire foot as a rigid body, motion from within the foot bleeds over and looks like ankle motion. So imagine there's a torque about the ankle. The ankle is not actually moving, but there is motion within the foot. If you have markers spread out over this foot, the motion from the foot, angular motion, gets multiplied by the torque, and it looks like power or work that's not really there. So the question is, does this matter? And in a nutshell, here's the plot that really caught my attention. This is ankle power over the stance phase of walking. This is one subject, the same data, either placing markers spread over the entire foot, so treating the foot as a rigid body, that's the red line, or just tracking markers on the back of the foot, the calcaneus. So this is where your calf muscles, the soleus and gastrocnemius, insert. And you can see that there's a marked difference in how much power is generated about the ankle. So whether you are a person that does motion capture and are trying to understand biologically what's happening at the joint level or the muscle tendon level, or whether you're someone who is designing exoskeletons or prostheses or walking robots, whether you're trying to mimic what biology is doing or whether you're just trying to compare back to some baseline control of what the human is doing, we shouldn't be off by 50 to 80%. And if you look at these estimates, that's often where we're at. I'm not going to go into all the details as to why we trust this blue line more than the red line, but the short version is there have been some really detailed models where they place dozens of markers on the foot and track individual segments. That's the most direct evidence as to why we trust this blue line. There's also some converging evidence where you look at cadaver feet. So we can chat more about that afterwards. But long story short, our estimates can be off by quite a lot if we treat the foot as a rigid body. A related problem, so if you're looking at interventions such as testing different footwear or testing somebody in shoes versus an exoskeleton, if you apply something that changes the rigidity of the foot, then your model is less bad for certain conditions than others. Things that you measure, things that you see in your data may not be related to how someone is adapting to your device. It may just be related to how well each of your devices fits the model. So I'm running short on time, and I want to give one other example, which is particularly if you work on prosthetic feet, you should be aware of this. It's not exactly the same analog, but once you start having non-rigid components, if you treat the foot as a rigid body, you may look at two prosthetic feet and say, oh, this rush foot blue generates more power than the red foot, but if you were to actually take a more complete model, which doesn't make assumptions about the rigidity of the foot, and essentially measures the power between the shank and the ground, you may come to a completely the opposite conclusion. So the key is you can come to exactly the wrong conclusion if you're not careful about the models. The very quick summary of this is I recommend that we stop using this 120-year-old assumption. If you want more information, you can ask me about it, or you can check out our paper that recently came out. And then I'll just leave these up here for you to peruse as my summary of what Matt, Eric, and I have spoken about. Thanks.
Okay.
So if we make an assumption that most of the force that you apply to the ground is either at your heel or the ball of your foot, what's the difference between foot deflection versus ankle power for a walking gait?
The question is, what's the difference between foot power and ankle power?
So you wanted to divide, say we have a flexible foot, it's not all coming from the ankle, from the rigid body assumption. But if the forces you're applying to the ground are through the ball of your foot, then what does it matter? Why does it matter?
So the easiest way to think about why it matters is imagine a situation where you're let's say walking, and then let's say your ankle, so by that I mean the angle between your shank bone and then let's say the calcaneus, goes through a 20-degree range of motion. But then let's say in your forefoot there's an additional 10 degrees of motion. So if you wanted to know about how much power am I generating with my calf muscle tendon units, you'd want to know what's the torque that's generated by those muscles multiplied by the 20 degrees. But if you treat the entire foot as rigid, then that 10 degrees, some amount of it bleeds over, and you end up multiplying your torque times a larger number. So you get a fundamentally different number, and in some cases it can be a very bad misestimate.
So granted, and I believe you, but if I'm
Thanks.
building a robot, then I don't care about the morphology of a human.
You're right.
And so at that point, does it matter where it comes from? And should I build flexible feet for a robot? That's the question.
Should you build flexible feet for robots? So the two things you said is, one is you may very well not care. If you're not trying to mimic what the biological foot is doing, and you're not trying to compare back to what the biological foot is doing, you're just building your own robot foot, then I would agree. You don't necessarily care about whether us biomechanists get our estimates right on foot power versus ankle power. In terms of whether you should build flexible feet for robots, I didn't know this, but I discovered there is a fair amount of literature out there on that, where people have added toe joints or other flexibility into the feet. The models that I've seen, and I think Eric can corroborate this, do seem to suggest that there may be some benefits, but I've never implemented it, so I don't know some of the practical challenges which may not appear in the simulations. I would say it's an interesting open question, and I don't know if your robots have the same preferences as our people who seem to like toes.
Thanks.
If I can just add, I don't think you can know if it's important until you actually take it into consideration. That's one point. So Max had a question, and then Andy, and then I'll send it back out on the floor.
So it's more about the rigid body assumption of the foot and so on. And I guess my question basically is, the models are still wrong, right? Like, because it's a model, or this rigid body assumption of free due inverse dynamics. And so how much wrong is there left? You're getting closer, it sounds like, but is it like, how much do you trust this still? Is it still way off, you think, or?
So the question is how much, so after we take into account the non-rigidity of the foot.
Yeah, and before that, you're like, oh, what about the soft tissue, right? And so there's probably going to be another 10 things.
So I don't think there's another 10 things. There's probably another 100 or 1,000.
Okay, yeah.
But so there's different ways to evaluate how good do we think we're doing. One is to kick that onto the ground. So I would say one of the things that I find most compelling is looking at, if we add up all of our individual work sources, how well does that change? How well does our estimate of individual work sources at, say, the hip, knee, ankle, and foot match whole body energy changes? And at that level of looking at, can we account for all of the work sources which explain the energy change of the body, I think that we do quite well. So in other words, things add up very well considering imperfections in our measurement instruments. In terms of how well, at a single joint, how well does ankle work represent the work that's done by the muscle and tendon? We have the same problem continuously in biomechanics, which is we rarely have a ground truth to compare against. So we could probably check this in some animal models. It's really hard to check it in humans. There seems to be converging evidence that it's better, but I can't put a number and say, okay, now we're within 1% of reality or 10% of reality. We're not going to be off by 50 to 80% as we are now. Closer to 10%, less than 10 would be, if I had to do a hand-wavy guess as to where we're at.
I want to press you on Jonathan Hurst's question. So feet are different if they bend at the toes or not, but the question is, from a mechanics point of view, in terms of what's passed through to the leg, is there a difference that you think is important between a spring at the ankle and a flexible foot? And you didn't really give a sharp answer to that question, which he was asking.
So let me make sure I understand the question then. The question is there a difference between
having a spring, say, at the ankle between
so let me see if I can interpret.
Yes.
So the question also for the back, because I don't think the mic's working, is there an important functional difference? Clearly you're going to get the specific muscle wrong if you think that it's gone 30 degrees and instead it's only gone 20. But is there a functionally significant difference in terms of stability, control, energetics between bending at the ankle and bending at the toe? Is this
John, is that correct?
Yeah.
So maybe I'm going to pass it to Eric because maybe he can give you. So I can answer at a high level, but I was hoping you could maybe speak to the specific, how much was push-off change? So you can pick some biomechanical metric that you think is important. We can give an example of push-off work where you only change ankle stiffness versus change the springs.
That's a psychology experiment, not a mechanics experiment.
And I actually think this is going to divert. This is actually a really important question, but I think it's going to take more than a minute or two to answer.
Okay, I'll do the quick summary, which is just that there are.
We just heard from the usual suspects. I want to get one more question out.
There's mechanical models that suggest yes.
So my question is for Eric as well. Why exactly was it surprising that they didn't like it when the work that they were doing is actually higher? The conditions that you subjected them to, because in all of those cases the work was higher. So why is it surprising? And also you're only looking at ankle work. Maybe the total metabolic cost is higher or something like that, which is why they don't like it.
So that's a good point. So we haven't measured metabolic cost yet. So to me, it was surprising because usually for these assistive devices, it's usually the outcome metric is to input more energy, continuously just input more energy. Especially like I think current studies with Biome suggest that they want more and more energy storage or energy returned. And so that's why it was really surprising to me is that I would suspect that more energy return would be more beneficial or appear beneficial for the subjects.
And we're a bit over, so I have to stop it there because it's a long program and we're already half an hour or so over. So I'm going to turn it over to Jerry. He's going to tell us what we're going to do. 10-minute break. Be back here by 10 minutes from now.
You could